All right, so today, 6.4, proportional reasoning, is very much a culminating section of everything we've been doing in the other sections. Kind of pulls all the pieces together and incorporates many of them into how we can really use fractions, specifically when we're working out real life problems. So we're going to take a look at a little bit of vocab to start with, just a little bit today. We've talked about ratios. Ratio notation is written as A:B, which is fine if you're writing a newspaper article. Not typically the way that we see our mathematics. And so A divided by B in fraction form is how we write it. And we read it as A to B. There are two different types of ratios that we talk about. We talk about ratios as part to whole and ratios as part to part. Here's an example. If you had 15 students in the class and 7 of them made an A, then the part to whole ratio, that is the A's compared to the whole class, would be 7 to 15. That's one comparison. The other comparison you could make is the A's compared to the not A's, and that's a part to part comparison. And if that's what you were doing, the ratio would be 7 to 8. Okay? They're both descriptive, they just describe something that's slightly different. So we're going to do an example of boys to girls in a classroom. This one says, if the ratio of boys to girls in a class is 2 to 3, what is the ratio of boys to all the students in the class? So if I have 2, I'm going to write it this way, 2 boys compared to every 3 girls, then what would I have if I compared boys to the total of boys plus girls? Two to what? Yeah, 2 to 5. So we're not really saying we have 2 boys and we have 3 girls. Like, that's not what's being said. But it is a reduced ratio, likely, of what's going on in the classroom, right? So like maybe there's 10 boys and 15 girls. Okay, well then that's 10 boys compared to the 10 plus 15 girls. I'd still end up with a 2/3 compared to a 2/5 ratio at the end. So we can write it as 2/5 like this, or you could write it as 2 compared to 5 like this. Okay, does that make sense? We talk about these things like this all the time. Sometimes changing in and out of them we can get a little confused if we're not thinking about them in the right way, though. So let's do it the other direction now. This one says if 3/7 of the class, right, girls compared to the whole class, what is the ratio of boys to girls? So we can still think of it, it really helps a whole lot if you put some units on where they are. This is 3 girls compared to the girls plus boys. And what I'm asked to find is the boys compared to the girls. So the girls is the 3 I already started with. But what would the boys number be represented as? 4, right? So of this one who are girls and boys, we know that there are 3 girls. So the other one must be 4 boys. So there's 4 boys. So this is a 4 to 3 ratio, or you can write it as 4 to 3 like that. All right, a proportion, because that's the whole point of this section. A proportion is a statement that 2 given ratios are equal. So this would be a proportion. We have one fraction on the left, one fraction on the right. We have an equal sign between them. This is a proportion, equality of a ratio. There are 3 theorems about the relationships within a proportion. Theorem 620 says that if we have this proportion, A over B equals C over D, that this will only hold true if I can multiply across the diagonals and get the same value. That makes sense. That's one of the ways that I talked about being able to compare fractions and see if they were equal, right? Back in 6.1 maybe, or maybe it was 6.2. We talked about comparing fractions like this. And so that's what you see. AD, A times D, equals B times C. So if one of those equations holds, the other one holds as well, and vice versa. Theorem 621 says, again, if A over B is equal to C over D, that there's another ratio proportion that we can set up, that B over A is equal to D over C. Comparing these two, what did we do to get that second ratio? Yeah, we flipped fractions upside down. And we all said, well, yeah, that should work, right? If you flip them both upside down, they should be the same as they were on the other one. Well, of course they should. And if you weren't quite sure, if you cross multiply, you of course get the same cross multiplication equation you got up here. So from that perspective, it also makes sense that this would yield an equivalent proportion. 622, another equivalent proportion, A over B, C over D. And it's now comparing A over C to B over D. This one's not flipped upside down. So what happened, what changed to give us this new proportion? Comparison. Gracie, you want to tell me something? I can just tell.
I just say C and B just swap.
Yeah.
What you're studying across multiplying.
Yeah, so those are both things I wanted to actually say. You've said two things. That's fabulous. You bet. So looks like C and B flopped. They switched places, and they did. We'll actually see some concrete examples of how that happens in word problems and why that makes sense sometimes to see happen. But that's exactly what happened. And you're also right. If you actually cross multiplied, it gives you the same equation, right, as you get from the very first one, 620. So again, that should make sense. And while I don't have an equation that says this, it's also equally true that I could have flipped the other diagonal. Like I could have written D over B equals C over A, right? I could have switched this diagonal just as easily as the other diagonal. There's nothing special about which diagonal is being switched. Not only that, but you could switch the diagonals and you could flip them. Crazy stuff. All those are actually viable options for creating equivalent sets of proportions. All right, so we have some examples of proportions and how we can think about setting them up. We have Jim. Jim found that after working for 9 months, he had 6 days of vacation time. If he accrues vacation time at the same rate, how many days would he earn in 2 years? So here's the thing about proportions. Proportions are always ratios that are comparing things. And anytime we're dealing with a word problem like this, there's always going to be two comparisons being made. So let me identify with you on this one what's being made, the comparisons. One comparison that's being made is days off compared to, I'm just going to write it actually this. Compared to months worked. Okay, do you guys see that they're making a comparison between those two in their descriptions? Yeah, definitely. The other thing that's being compared in this one is his current days of vacation, right? And it's being compared to his future. Okay, so these are the two comparisons. One is comparing days to months, right? Days off, months worked. The other comparison is comparing now to in the future. So whenever you're setting up a proportion, one of those comparisons is going to be the tops and the bottoms of the fractions. The other comparison is going to be the two sides of the equations, and it doesn't make any difference which ones you pick where. So we're going to set this one up in both ways just so I can show you that it doesn't make any sense. Not sense. Doesn't make any difference. That's what I wanted to say. It does make sense. Doesn't make any difference in how we set it up. So my first one was days compared to months. So we could do days and months as the tops and the bottoms of the fractions. And then we can compare now to later across the two sides of the equal sign. So right now, how many days does he have? 6 days. In the future, we actually don't know how many days he has. That's what we're trying to find out. So that's the unknown piece. Okay, so now, current times. How many months has he worked? 9 months. In the future, the date we're looking at, what's the number of months that he's been working? 24. So be careful. They still has to be in months. You can't put 2 years there. You have to put the 24 months mark. And then we can actually take a look at what happens as we cross multiply. So I would ignore the units in the moment. We know that the ending answer is going to be a number of days because that's what we're looking for. But I have, in terms of the values, 6 times 24, and it has to equal 9 times x. So grab a calculator if you don't have it out yet. What is 6 times 4? 24. 144. And then what would I do to find x? Yep, I would divide by 9. And what would I get? What would I get? 16. It's 16 what? Days. So in the end, we definitely need to have units on all our answers. So this is what it would look like if I set it up with days and months as the top and the bottom, now and later on the sides of the fractions, okay, the sides of the equal sign. Let me set it up the other way so that you can see how it looks on that one. So I could have instead set it up so that it was days on the left and months on the right, and now on top compared to later on top. And there's nothing special about now being on top and later on bottom. You could switch them if you wanted to, doesn't matter. Or days being on the left and months on the right, you could switch those and it doesn't matter either. That would be fine. But how many days does he have now? 6, right? 6 days. Days later is what we're looking for. He's worked 9 months now. He will have worked 24 months later. And if you notice, you cross multiply, you have the same numbers you had before. Not only that, but if you compare what we just did, what appears to have changed places in terms of the 6, 9, x, and 24? What switched? So is it? The 9 and the x looks like they've switched places, right? Here, the 9 and the x are right here, and over here, they've switched. So it's actually that last theorem. That's why those theorems are going on, is because the setups actually can be set up differently and still give the same equality of ratio, a proportion, in a different format. Okay, so a couple different ways you can actually set it up and solve it, all yielding the same answers. Any questions on that one? Okay. Example number 4. On a city map, a rectangular park has a length of 4 inches. If the actual length and width of the park are 500 and 300 feet, respectively, how wide is the park on the map? So every time you're setting these up, you're trying to ask yourself what's being compared. And you're always looking for 2 quantities they're comparing. So somebody give me one thing that's being compared here. Okay, so how about, you said the inches and the feet? Is that what you're saying, inches and feet? So I'll describe it just a little bit differently, but it's actually sort of the map size versus real size, right? And the map, you're right, is in inches, and the actual real life is in feet. So that is what's being compared. Feet's on my screen. It's just going to take it a minute to pop up. So let's keep going. What else is being compared here? Say it louder for me, Jaylee.
Length and width.
You got it. It's length and width. Absolutely. And again, doesn't matter whether it's on the left or the right, but one of them on the left and one of them on the right. I was writing right. Length and width. Okay, so these are my 4 pieces I'm going to fill in now. So the first piece is the length on the map. So what is the length of the park on the map? 4 inches. Underneath, what is the length of the park in real life? It's the 500 feet. If you aren't sure, there's a couple things. First, length is usually considered the longer of the 2 measurements when you have a length and the width. But also they did them in order, length and width, and then here's length and here's width. Okay? So the length is the 500 feet. Okay? How about the width of the park in the map or on the map? That is what we're solving for. So call it W if you want, call it X, it doesn't matter. Give it a name. And this is my feet. I'm sorry, inches, because I'm on the map. And then what is the width in real life of the park? 300 feet. Wonderful. Again, other ways we could set it up. This one works just fine, so we're going to go with it. We'll cross multiply. 4 times 300 is 1,200 equals my 500 W. And then what? Yep, we're going to divide by 500. The zeros cancel nicely. Remind me to tell you something here just a second, too, if I forget. So I really am equivalently have 12 divided by 5, which is what? 2.4. Now, I realize that this whole section is working with decimals. I mean, it's working with fractions and not decimals. However, I contend that it still makes sense to go ahead and leave this in decimal form, because if you told somebody this in fraction form, it feels awkward for the context. Does that make sense? So this is sort of one of those things where it overrides the fact that we happen to be in the chapter about fractions. It just doesn't contextually work quite as well to talk that way. So the answer is 2.4 what? Inches. Any questions on that one? Okay, the next one is much more interesting in the sense that it's not quite so direct. Yeah.
So we were to do it the other way, like that's kind of like the natural way that I think of it.
Mhm.
Would you still want us to write out, like, in regards to work, like the, like, map size, real size thing, but just like in the other form?
Yeah, you'd have map and real size on each side of it. And I mean, Emma originally said inches and feet. You could label it that way. It wouldn't hurt anything if it helps you to keep track of it that way without even saying map versus real life. That's fine. But you'd label at the top of each side of the equation, and then you'd label on the top and bottom of the fraction length and width, or vice versa. Okay, let me actually show you something that happened, and it was actually, this has been several semesters ago, like maybe, it may have been like 4 or 5 years ago at this point. They all started to run together after you start teaching. Y'all will all know about that soon enough. Is that you saw me cancel out zeros, right? 1,200, 500, I canceled my zeros, and that's perfectly appropriate and correct. But you can't do that with every number. And here's what the student did. I'm making up the numbers to some degree, but this is the equivalent of what they did. Okay? And it was on a final exam of the class, and I just kind of wanted to fail them almost because it was such a blatant bad mistake. Okay? Obviously, I didn't fail them for that. But the only reason I get to cancel zeros is because canceling zeros is the equivalent of dividing the top and the bottom by 10. Canceling nines is not the equivalent of doing anything to the top and the bottom equivalently. So this is a big no. You don't get to cancel any other number the way you cancel zeros. Zeros are very special, okay? All right. All right, this is an interesting one. Okay, so we have Kierra and Dora. Kierra and Dora worked 3.5 hours and 4.5 hours respectively on a programming project. They were paid a total of $176 for the project. Because Dora has fairness as one of her strengths, how many of you have fairness from the strengths binder test? Any of you? Did you guys do that in your school? Does nobody have fairness? I do. It is one of my top 5. Yeah, it's a big deal in my mind. It shouldn't be. I know life's not fair, but I want things to be fair as much as they can be. That's my problem. Okay, but she has fairness as a strength, so she wants to make sure each of them are paid according to the time they spent. So one option is we could just split the $176. They both did part of the project and they each get the equal amount, but that would not be fair because one of them did an hour's worth more of work than the other one, right? So our goal is to try to split it according to the time that they worked instead of according to the fact that they both did a portion of the project and say it's 50-50. All right, so there's actually a couple of ways we can set this up that are distinguishably different than we were talking about over here, actually really truly different. So one of the ways that we can set them up that's probably the most natural looking at the problem from the get-go is to compare Kierra and Dora. Okay, whoops. And then what else could I compare? Or what else is being compared? How much they worked compared to what? Yep, how much they get paid. And you may be looking at this and saying, well, how else would you set it up? I'm going to show you in just a minute. Because this way that's most natural to look at it is the least natural for what I'm going to have to fill in on the blanks. So the amount that they worked, that's fine. How much was Kierra's? 3.5. If you want to write 3.5, fabulous. You can write 3 and a fraction on half if you prefer. How much did Dora work? 4.5 hours. So far, nothing weird. What's the problem on the other side? Well, they weren't both paid the same, but they were paid in combined, right? Is that what you meant to say, Emma? Yeah. Right. So we don't know how much either one of them got paid. But I don't need 2 variables in the equation. That is super not going to be helpful. I'm not going to be able to solve it if I put an x on top and a y on bottom. I don't want to do that. So here's what I can do instead. I can say that Kierra made X dollars. And then I can say that Dora made 176 minus X dollars. It's a little awkward, but do you see where the number, why that would be true? Okay, but it's awkward, right? It's awkward. Let's go ahead and solve it so you can see how it looks when you solve this particular one. So I have the 3.5. I need to be careful because the 3.5 actually has to be multiplied by the 176 and the minus x. So that's also a little awkward. Everything else was single, multiplication pieces. And the other one is 4.5x. So I have to distribute the 3.5 through, which gives me, I think, 616, if I'm looking at my paper right, minus my 3.5x equals 4.5x. What next? Add 3.5x to both sides. So you have 616 on the left. What do you have on the right? 8x. And then what would you do? Divide by 8. So are you guys now seeing why this problem is so much more challenging than the other one? It is. What is 616 divided by 8? It is 77. Now let's answer the questions that are asked specifically. That is, how much does Kierra make? And how much does Dora make? Okay, so Kierra makes 77. How do I figure out what Dora makes? 176. What is 176 minus 77? So she makes $99. And it's not a bad idea to go back up and make sure that makes sense. It says Kierra worked 3.5 hours. That's less than Dora, and Dora worked 4.5 hours. So Kierra should be making less money than Dora. You can at least visually sort of make sure it makes sense at the end. So the last thing we'll do today is let me show you how this ends up if you think about it in a slightly different way. Whoops. Trying to make this a little bit smaller so I have more space to work. Okay, so this is my answer when I'm done here at the top. So instead of comparing Kierra to Dora, I could be comparing Kierra or Dora, doesn't matter, but I'll use Kierra since she's listed first, to the total, like Kierra and Dora combined. So kind of instead of comparing part to part, Kierra's part to Dora's part, I compare Kierra's part to the whole project. So I can still compare their work to their pay. But instead, Kierra worked 3.5 hours. And the total that both of these young ladies worked is the 8 hours. Right? And then I don't know what her pay is, but the total pay was $176. So it's more awkward in the sense of thinking Kierra compared to a total, but the mathematics is a lot cleaner than the other one. Because when I multiply, I don't have to do any distribution. I have 8, x, and I have that 616 that I had a moment ago, like immediately. So the x is the 77 dollars. And of course, we still get then go back and find Dora, and Dora is giving me going to be the $99. Okay, so for this semester, for fall 2020, we are going to push that test back to Friday because I haven't finished this section. I want you to have time to do group work on this section, and I want you to have a legit review session. So if we have to crunch something later on, at least we're not crunching the section on fractions. So that's what our plan is. So over the weekend, you don't have anything you have to actually be making progress on at the moment, okay?